CBT Nugget's Network Plus series, Wireless Technology. Well, for decades now, local area networks have been typically limited to physical wired segments. But with the emergence of technologies that utilized infrared IR and radio frequency RF to carry data, local area networks have been set free from the limitations of the physical media. We're going to explore that freedom in this nugget on wireless technology. In this nugget on wireless technology, we're going to cover 5 main areas. We'll first of all compare wireless LANs to conventional local area networks. Then we'll look at the characteristics of wireless local area networks radio frequency. We'll talk about the wireless LAN standards. We'll explore wireless LAN security. And then we'll talk about implementation and configuration of a wireless access point. I think one of the best ways to understand a wireless LAN is to compare it to the local area network, the wired Ethernet network that we spent so much time talking about already in this Network Plus series. Wireless LANs use radio frequencies at the OSI physical layer 1. We know that Ethernet uses a wide variety of different cabling. RFs are going to use radio waves. Wireless LANs use what's called CSMA, carrier sense multiple access, with collision avoidance. So it's still the carrier is sensing, in this case it's sensing the RF area, it's multiple access, there's multiple nodes trying to get access to this network, but it's collision avoidance. Collision detection isn't possible in a wireless local area network because the sending station can't receive at the same time that it's transmitting. That's what we do in an Ethernet. Therefore, the wireless station can't detect a collision. So, wireless LANs use these protocols called ready to send. These are special kinds of frames that are sent through the airwaves. Ready to send and clear to send mechanisms that are part of CSMA-CD to avoid their collisions. Now, I just mentioned frames. Wireless LANs actually use a different frame format than a wired Ethernet LAN. As a matter of fact, wireless LANs require a bunch of different information in the layer 2 header of the frame. And there are many different types of layer 2 frames depending upon the implementation. Because think about it, mobile clients, for example, often are battery powered, and so they have different power levels. And because there aren't physical connections to the network, there's more information that needs to be shared between the wireless access point or the wireless hub and that wireless end station. Most Ethernet communications now is going to be full duplex communication, where you've got a laptop or a workstation that connects to, ultimately, a layer 2 switch, a layer 2 or multi-layer switch that actually creates a full duplex communication between the station and the switch and does all of this bridging on the back plane of the switch. Wireless LANs are half duplex communication, kind of like a walkie-talkie, only one device can communicate at a time. RF also has some unique issues. We know that we have to deal with things like crosstalk and interference in a wired Ethernet because we know we have the pairs that are twisted paired copper wires to help us combat interference and crosstalk. But we've got more things like interference from other things that use the RF, like baby monitors and microwave ovens, ham radios, CB radios. We have noise, we have convergence issues, and we have privacy issues. We're going to talk about security later on. But because the radio frequency can reach outside of your building or the facility, you're going to have privacy security issues built into that as well. Wireless access points are really shared segments like an Ethernet hub, so they behave more like a hub and a lot less like a switch. We don't see Ethernet hubs used very much anymore. And then finally, wireless LANs, as opposed to local area networks, have to meet country-specific specifications. So if you're in Japan or in Europe or the US, you're going to have different specifications for your wireless equipment based on those government standards. Now, radio frequencies are radiated into the airwaves by antennas that create radio waves. We could have antennas here on our access points. An antenna could also be mounted up on a wall or dropped from a ceiling or outside of a building. We also have antennas built in typically behind the monitor panel on a laptop, or on a laptop or workstation. It could be a PCMCIA card, it could be a network card that goes into a slot, it could be a PCI type wireless card. So those are the antennas. And RF is still kind of mysterious to us. We don't completely understand the physics behind it, but if you want to think of an antenna as kind of like the speaker on, let's say, your stereo or your home entertainment system, those speakers, the way that sound is pushed out of those cones, kind of similar to that. Now, obviously, objects can have, because of wireless, can have different types of interference. Reflection occurs when an RF wave bounces off an object, let's say like a planter that has plants in it, or an elevator shaft, things like that, metal or glass surfaces. We can have scattering when the RF wave strikes an uneven surface, for example, like a rough surface, and absorption when the RF waves are absorbed by objects, for example, like walls and carpeting. And by the way, these are wired connections from a multi-layer switch or a controller to my wireless access points, and these are my RF waves. It's not smoke. I know it looks like I have laptops that are on fire, but that's not the case. Now, there's some rules for data transmission over RF, okay? If you have a higher data rate, you'll have a shorter range because the receiver needs a stronger signal with a better signal-to-noise ratio, SNR, to receive the information. If you have higher transmit power, that'll result in greater range. That's governed by the FCC. Higher data rates require more bandwidth. Increased bandwidth is possible if you have higher frequencies or more complex modulation schemes. And higher frequencies have a shorter transmission range because they have higher degradation and absorption. Remember, absorption occurs when RF waves are absorbed by objects like carpeting and walls. You can get more efficient antennas to overcome that. Now, this is a CSMA-CA environment, so you've got a particular area that a wireless access point covers. And one of the phenomenon here is this: the more devices you add into this area, then ultimately the lower amount of bandwidth that's available. Remember, they're contending for a finite amount of bandwidth. Also, the farther away you get from the access point, the worse your bandwidth's going to be. So devices, remember I talked about we had frames that are being sent over these RF waves. Well, in these frames, there's a negotiation process that happens between the access point and the laptop, for example. As more devices are added to the area and authenticate to this access point, then these particular devices can drop back in their bandwidth. They'll renegotiate to 2 megabit per second, then back to 1 megabit per second. As they get farther away in those frames, they'll negotiate down from 54 megabit per second to 24 megabit per second and then down. And this is all handled by the special types of frames that RF uses. Now, there are three main organizations that define wireless LANs. You've got the ITU-R, that's the International Telecommunication Union Radio Communications Sector. This regulates the RF that's used in wireless. We have the IEEE, the Institute of Electrical and Electronic Engineers. This is going to be governing our 802.11 wireless technical standards. We know Ethernet is 802.3 with a bunch of letters after it. We have 802.11, also followed by some letters like A, B, G, N, I, and many others. Then we have the Wi-Fi Alliance. The Wi-Fi Alliance is a global nonprofit industry that certifies devices and promotes wireless growth through interoperability certification worldwide. Now, the good news is for your exam, you don't really need to know any physics or hardcore RF technology for the exam, but you do need to understand that wireless And RF operates in different bands, different frequency bands. For example, audio operates down here in the extremely low to low band. You've got your AM radio broadcast, shortwave radio or ham radio, going up to FM broadcast, television, cellular. You've got infrared way up here. Then we start getting into visible light, ultraviolet, and X-rays. We're operating right in here in the ultra-high, super high bandwidth. So there are three unlicensed bands that we are talking about here. You've got the 902 to 928 megahertz band. We've got the 2.4 to 2.4835 gigahertz band. And then we have the 5 gigahertz band. So you need to memorize especially this one in green and this one in red, because this particular 2.4 to 2.48 gigahertz is what governs the very popular and ubiquitous 802.11b and .11g wireless standards. 11a, which isn't used as much anymore, is going to operate in the 5 gigahertz range. So we want to focus on .11a, .11b, and .11g. There is a .11n that's out on the shelves now, but we don't care about that for our Network Plus exam. .11a, as we know from up here, operates in the 5 gigahertz frequency band. We have up to 23 channels which are available to us. That's because of the type of transmission modulation we use. We use what's called OFDM, which is orthogonal frequency division multiplexing. The different data rates that we get can be 6, and I'm going to write them all out here: 6, 9, 12, 18, 24, 36, 48, and 54. Now, this is just the theoretical maximum bandwidth. This is a contention-based or half-duplex environment, so you're really only actually getting about half of this bandwidth. But why do we have so many different values here? Well, remember the diagram I showed you earlier. The more devices you add to the area that the access point is servicing, well, the less amount of ultimate bandwidth you have to divvy up among all these different nodes or stations. Also, the farther away that my laptop gets from the access point, I have to kind of negotiate down from 54 to 36 until all the way down to 6 until suddenly I'm just out of range. Now, .11a isn't used as much anymore, and a lot of other devices use .11a's 5 gigahertz range, so you do have some interference problems there. .11b is very popular. This uses the 2.4 gigahertz range, frequency range. You have 3 channels available to you. There's actually more, but you don't want them to overlap, so typically you're going to use 3 of the available channels. It uses for its transmission modulation type DSSS, which is direct sequence spread spectrum. You don't have to know how these particular modulation types function for the Network Plus exam. The data rates that we have are going to be 1, 2, 5.5, and 11 megabit per second. Again, because of half duplex and CSMA-CA, we're only getting about half of that in reality. And as we know, the same thing applies. The more stations you have, the less ultimate bandwidth you have, the farther away you have, the frames will go through a renegotiation process. It can also be related to power as well. Finally, we have .11g, also operates in the 2.4 gigahertz range and allows for 3 non-overlapping channels. However, .11g is backward compatible and it's quite flexible. So it's backward compatible with 11b, so it can also use DSSS for its modulation, but it also uses for its higher bandwidths OFDM that I mentioned earlier, the same modulation type that .11a uses. And with OFDM, if you're using DSSS, you're going to get these type of bandwidths. If you're using OFDM, you're going to get these type of bandwidths. So using .11g and using OFDM, you're going to get much higher bandwidths. If all of your stations in your area are using 11g, you will get to benefit from these higher bandwidths. If you have an area, let's get that diagram back up here. So let's say this access point is going to create a area It'll have an SSID or an identifier called Nugget, and we're going to be a .11 .11bg access point. What that means is if this particular laptop's using .11b and these are using .11g, then we're going to fall back and use the modulation type for 11b, so the maximum bandwidth we're going to get is 11 megabits per second. Even for these G stations, even though they have much higher capabilities, they have to use the other type of modulation and kind of least common denominator to communicate within this area. And again, with 11B and G, we've got 3 possible channels, so most likely this access point is going to make this area channel 1 or channel 6 or channel 11. There has to be 5 channels in between them to create an overlap. So if you've got a BG network here, this is going to use 1, 6, or 11. Let's say they choose to use 6. If this area is right over here, maybe this is the second floor of the building and this is the third floor of the building, or a different area of the campus, if this is using channel 6, then this .11bg network is going to have to use channel 1 or channel 11. Next, let's talk about .11 topologies, and there's really 2 major modes, and then within one of those modes we can break it down into 2 different types. First of all, you've got what's called ad hoc mode, and I'll just come over here. Ad hoc mode, which means kind of as needed or on the fly. This is what we also refer to as an IBSS, okay? An independent basic service set. And an ad hoc mode would basically be between these 2 laptops. Kind of like an infrared port that connects 2 laptops together. This is 2 mobile clients directly connected without some type of intermediate access point like this one up here. This could be done between 2 laptops in an airport or a coffee shop, a thing like that in your small office, home office. Windows make this really easy to set up with their peer-to-peer networking capabilities. Coverage is limited, and everybody has to be able to hear everybody else. You don't need an access point, and the drawback is they're really, really difficult to secure. Now the other mode is called a BSS, or a basic service set. And that's what we see here with this access point, wireless access point, and these devices. This is one of the most common in the small office, home office, small to medium-sized business. Now, the basic service set is part of what we call infrastructure mode. Okay, so this is ad hoc mode, IBSS. This is infrastructure mode because there's an infrastructure. There's a wireless access point that is the basically .11 hub that handles the CSMA CA half duplex communication between all the nodes in the area or multiple areas. So the devices that create a BSS are basically mobile devices using a single access point to connect to each other. They can also use this to connect to other wired resources, for example through the switch or multi-layer switch. The BSS is the fundamental building block of wireless topologies. The BSS access point is uniquely identified through an SSID, or in this case it would be a BSSID, the service set identifier. As I mentioned, you can use something that's very complex, a meaningless string of alphanumeric characters, or we could go ahead and name this something like Nugget, or Nugget WLAN. If you go and you buy a particular access point or a wireless router from, Best Buy, for example, from Netgear or Linksys, it'll automatically have a default SSID. So the SSID basically is a network name for this service set. It's user configurable, and it can have up to 32 case-sensitive letters. Now the other type is what we call an ESS, or an extended service set. And this is when you have the wireless topology extended with 2 or more basic service sets, as we see here, with some type of distribution system. In this distribution system that we're looking at here, this could be, let's say, some type of Cisco wireless controller So this could be a wireless controller that's in, let's say, a wiring closet of a hospital, and these are thin access points that are basically hanging from the ceiling or connected to walls throughout the medical center. And you've got this distribution system. It could also be a modular switch or multi-layer switch. It provides a wired infrastructure. Remember, a lot of times your wireless network will have to be able to communicate to another wired Ethernet. Also, you want to use this ESS, this extended service set, so a client, let's say on this laptop, can actually come over here and roam over into this service set. When they do, they'll have to renegotiate to this particular access point. Maybe they have to get a new DHCP, dynamic IP address and configuration, and other settings. So you want to have this back-end communication through this controller or this layer 3 switch that manages this backbone for these wireless access points. So if we're going to have an extended service set that moves beyond just the basic service set of one access point, then we're going to have to think about overlapping. So for example, if this is a .11 BG network, which is the most common, then we're going to have to decide this particular cell, we can call this a cell or an area, okay, is going to be either in using channel 1 or channel 6 or channel 11. This one's going to be using channel 1 or 6 or 11. So let's say we're using channel 1 for this cell or area, and we're going to use channel 6 for this cell or area. Obviously, as a device roams from one area to the other, it's going to have to renegotiate and move over and start using channel 6. Now, it's recommended from a design standpoint that if you do this in your organization or your building or for a customer, you want to have about a 10 to 15% overlap, so that as the station roams from one area to the other or one cell to the other, there's no loss of communication for that period of time. And again, all this negotiation can be happening either directly between these two access points, or you can have some other type of infrastructure with a wireless controller or a layer 2 or layer 3 modular switch. Now, one of the interesting characteristics of .11 is that it was basically constructed to be very open and promiscuous. For example, any wireless station that can come into a particular area of an access point, by default, can use what's called open authentication. And since that SSID number, for example, Nugget, is by default advertised in beacon frames throughout this area, any device that comes in range can basically do an open authentication and start communicating with this wireless access point and the other stations that are in this particular area, and even beyond into the Ethernet if so configured. So that's the basic default behavior, and again, it was designed that way because it was meant to be more of a promiscuous, open type of communication. However, you can see from that it's an unsecure environment, especially for the corporate network, or maybe a medical network that deals with privacy information, or government or military networks. So let's talk about some of the ways that we can secure this 802.11 wireless LAN. Now, this is going to be a pretty brief section here of this nugget. Let me tell you why. Later on in this Network Plus Nugget series, we have several dedicated nuggets just on network security, and we're going to define things in greater detail on security. So I'm going to be introducing some concepts here and some technology and terminology that may be totally foreign to you. So you may have to come back and review this wireless LAN nugget after you go through the security nuggets at the end of this series. So that being said, don't get overwhelmed by the terminology here, okay? We're just going to talk about the basic fundamentals of wireless LAN security. Now, the way I want to do this is kind of with a timeline. Now, if you'll notice, the timeline only goes back to 1997. So what that should tell you is this really isn't that mature of a technology, especially in its use in the corporate environment. And combined with modern networking. So we're going back to 1997, where we had what was called Wired Equivalency Privacy, WEP, kind of misnamed. The goal here was to get privacy and security that was the equivalent of what you got on the wire, but it just didn't do it. This is the initial 802.11 security, okay? And it used 64-bit WEP keys for both encryption and authentication. It was basic encryption, okay? It had no strong authentication mechanism built into it. The keys were static, and because they were static, they were breakable with fast processors. It wasn't a scalable solution. They didn't have mechanisms in place to be able to do this on an enterprise level. We could use some other features, for example, like MAC filters. You could tell the access point, hey, you know what, access point? I only want you to authenticate and associate with certain MAC addresses. The problem is there's plenty of tools out there that will allow you to masquerade or spoof as another MAC address or even change the MAC address. Okay? So we relied on that. You could also tell the access point, hey, don't advertise the SSID. Don't advertise the name of our area to make it easy for open authentication hosts to authenticate and authorize. But that wasn't a very good method either, because the SSID was sent in other types of .11 frames as well. So WEP, you may still see it being used, okay? I'm going to draw a line here, in small office home offices, which is okay, but it's not a secure solution for the business. In 2001, 4 years later, implementing 802.1x EAP. This is basically a new security standard for port-based authentication. 802.1x actually works with, let me just jot this down here, .1x actually works on top of 802.3 and .11. So you can use this port-based authentication, authenticating the device based on its port, which is an RF port, .11, or a physical port, Ethernet, .3. Then you could use some type of database, either on the authenticating device, or maybe you could use a radius server on the back end to have a database of mappings for the clients or the hosts, the stations that you want to participate on your network. EAP stands for Extensible Authentication Protocol. And this is basically a way to create an extensible mechanism to have all different types of authentication mechanisms that worked with .1x. So you could say, you know what, we want to use certificates, or we don't want to use certificates. We want to use certificates on the server side but not the client side. Things like that. So what .1x gave us, it gave us dynamic keys. So we could dynamically generate that alphanumeric keying information for this process. No more static keys. You also have improved encryption, as you can use newer encryption algorithms. We'll talk about those later on in this Nugget series. And then, of course, EAP was very flexible. We could use different versions of EAP. We could use LEAP, that Cisco came up with. We could use PEAP or PEEP. We could use EAP TLS, which gave us kind of a public key infrastructure, certificate-based, and it could work with, as I mentioned, a back-end radius server as our database. That was 2001. In 2003, we started to see the WPA standard. WPA stands for Wi-Fi Protected Access. So obviously, this is part of the Wi-Fi Alliance solution. So WPA was a standardized solution, so global standard. It also improved the encryption mechanisms that we could use. It also used strong user authentication. It used LEAP, it used PEEP, it used EAP TLS, and it also used a new mechanism that Cisco provided called EAP Fast, which was a replacement for its LEAP that had some security issues, and EAP Fast gave you strong encryption without having to use a certificate-based solution. And then in 2004, we have this is the solution that we use now, which is 802.11i, or also known as aka WPA2. This is a 2 not a Z. This is the most secure solution. This is the one that we have available to us now. It uses strong AES encryption, so it supports this super strong standard that has different key sizes, 128, 256, for example. It has incredible authentication mechanisms, and it provides dynamic key management. Okay, that's all we're going to say about the kind of evolution of wireless LAN security. As I mentioned, we're going to talk about security in greater detail later on in this Nugget series. Let's take a look now at some of the basics of setting up a wireless access point. Okay, I've gone ahead and connected to my Zoom wireless DSL router, which is indicative of a lot of the ones that are out there, Linksys, Netgear, the small office, home office. This is a good example. And I went ahead and just connected to the IP address from this workstation. And again, you'll have instructions with your device on how to do this. And each of these different setup interfaces may look a little bit different, but I'm going to go to the wireless area here because we're going to focus on the wireless setup. Now it says the wireless status is enabled or disabled, so I can go in here and disable this wireless access point. If you aren't using strong security and you're leaving for vacation, you may want to go ahead and disable your wireless router. This is the SSID. This is the identifier. Now this is the default. And each one of your wireless access points will have a default SSID. And so you may want to change that to something that's not going to be so easy to guess, okay? And there are plenty of websites out there that identify what the default SSIDs are for all the products. And it may even be listed on the actual box itself. Now, this is one of the security mechanisms that was kind of all you had in the early days of web security, and that was to hide the SSID. This is a false, I'm not hiding it, okay, because it's a false sense of security. I could say true, hide my SSID, which means it's not going to send this out in a special frame type called a beacon. So if somebody is using their wireless client and they're searching for a wireless network, then my Zoom network will not show up on their particular screen. But if I'm using something like AeroPeak, which is a wireless sniffer, I'm still going to see it because the SSID will still be in other types of frames, okay? But this is one kind of basic way to create security so that somebody just can't drive by in front of your house and connect to your wireless access point. Now this is a 11G and B device. So you can see I can say 11B, 11B and G, 11G only. I'm going to use both. So as I mentioned earlier, if I in this particular area, which is channel 10, you can see there's my channels 1 through 11. In channel 10, if I have other devices in this area that authenticate and they're using B, then all of the nodes kind of drop down to B, which is not a good thing. For encryption, I could go back and use the original WEP 64-bit or 128-bit. WEP 128-bit is fine for a small office, home office. You're not going to generate enough traffic for someone to be able to probably crack that anyway, as long as you use a strong passphrase. But I'd like to see you use WPA, or as I mentioned, the strongest is WPA2. This is 802.11i. So those are the options I showed you earlier. Now your passphrase, and by the way, I have deleted mine because I don't want you to see it as if it really matters, but the passphrase should be strong, okay? It should be at least 10 characters, and you want to use uppercase letters and lowercase letters and numbers and symbols, okay? Have a strong passphrase. And of course, remember what I said, the region, this is important because your different countries out there, they're going to all have different RF standards. And so this is one of those things that separates wireless LAN from local area networking. Now I mentioned also that you can do wireless MAC filtering, where you could basically go in here and you could say, you know what, I want to add just the MAC addresses of the devices that I want to allow this device to connect to. So I could get the MAC address and add them in there. This is also kind of a false sense of security because these can be spoofed. Also, as I mentioned, you can do 802.1x authentication. Okay, and this is where you would pick a background radius server and have a kind of a database that could provide port-based authentication for those devices. So if you go to this, you're going to be able to use other mechanisms. Okay, so for the authentication server, I could say use the local database, or I could say a radius server and then put in the IP address of the radius server. It wants a shared secret because I need to have a password between this access point and the radius server so those two devices can actually authenticate. Okay, so that's .1x. Wireless setup, .1x, wireless MAC filtering, hide the SSID, and choose the right encryption type, preferably WPA and WPA2. That pretty much covers it, and that gives you a great look at wireless technology. If you want to go deeper on this, maybe just for your own knowledge, check out some of the CBT Nugget wireless security and wireless administration nuggets. All right. Okay, in this CBT Nugget on wireless technology for the Network Plus series, we covered 5 key knowledge areas. Looked at a comparison between LAN and wireless LAN, a good way to understand wireless LAN. Looked at some of the wireless LAN RF characteristics and topologies, the wireless LAN standards, a brief look at wireless LAN security, and then a walkthrough of configuring a wireless access point, or in my case, a wireless DSL router. I hope this CBT Nugget has been informative for you. I want to thank you for viewing.